Alright, in this video we're going to be talking about a person in an elevator. We're going to try to find the tension and some normal forces. Before we get into the details, let's go ahead and talk about what free body diagrams we could draw in solving a problem like this. Well, we could draw a free body diagram of the person, or we can also draw a free body diagram of the system, and the system includes the elevator and the person. Or we could draw a free body diagram just of the elevator. Now, with respect to part D, I know it's part D. Why are we going to do that first? Well, we can just go ahead and answer it because we have it all laid out for us, so let's just think about it. Do we know which way the elevator is moving? Well, we know the direction of the acceleration. The acceleration is downward. We have downward acceleration. The velocity might be downward. If the velocity is downward, then that means the object is speeding up. However, the velocity could be upward. The velocity and acceleration don't have to be in the same direction. In fact, every time something's slowing down, they're in opposite directions. So we look back at the problem statement. Does it say anywhere in the problem that the elevator is going downward? It does not. So this is a good review of Chapter 2. Alright, let's keep these different free body diagrams that we can draw. Keep those in mind as we move on to our solution on the next page. Alright, we'll start by drawing a free body diagram for the person. There's a normal force, and the person has weight. Now, tension doesn't show up on there, and tension is what we're trying to find. Well, it's one of the things we're trying to find. We're also trying to find a normal force. And so we need to draw at least one more free body diagram. So we'll draw a free body diagram of the system. Acting on the system, there is tension, and then there's the weight of the system, which includes the person's weight and the elevator's weight. Okay? We're not worried about the person pushing on the elevator or the elevator pushing on the person. Here, we're just thinking of this whole thing as a system, and we're not worrying about what we can't see behind our pretend blanket. I always imagine when I have a system that I just put a blanket over the objects in the system, and then everything behind the blanket is one thing. So that thing has weight, and there's tension pulling on it. Now I could also draw a free body diagram for the elevator, and this is where it gets interesting. The elevator has tension pulling up on it, and the elevator has weight. Now the elevator's weight is a little bit less than the system's weight. But then, what else is touching the elevator? The person is pushing the elevator, and the person is pushing downward. And that force is called the normal force. And if we look, this force here and this force right here, those have a special relationship. The elevator pushing up on the person pushing down on the elevator. Hopefully you remember, those are called a third law pair. Alright, now, how are we going to solve this? Well, we're going to use Newton's second law of motion. The planning part, as far as which equation to use, is so easy in these chapters. It's just, how do you apply it? And we've already done the hard work of figuring out all the different free body diagrams that are available to us. We only needed to draw two of those, but it's good for this one just to go ahead and draw all of them. So, which one should we do first? Well, if we want to find the tension, we know we need to pick one of these two. This one is simpler. We do know the weight of the system. We don't know the normal force, so this one would have two unknowns, and so we're going to look at it as a system first, then for the person. Okay, so let's go ahead and work on doing that. For the system, we say T minus 1,000 kilograms times 9.8. Okay, 9.8 is not the acceleration of the system. That's just a number that we're using when we're calculating the force of gravity, or weight, equals 1,000. Oh, and look, I made a mistake. Let's go ahead and correct that now. It said the weight of the system, and I put 1,000, but I just remembered the elevator has a mass of 1,000. The system has a mass of 1,090. All right, so I fixed that. And then on the right-hand side of Newton's second law, mass of the object or system, and so 1,090 times negative 2.8 meters per second squared. Okay, we know it was a downward acceleration, and so that ends up being a negative number. And let's see, I should have put that up here somewhere. Okay, up is positive, and it said it was downward. So now we can go ahead and calculate this. So t minus, we're going to punch this in on the calculator. You can try it along with me. I get 10,682 newtons, and then on the other side, 1,090 times negative 2.8 is negative 3,052. Now we're going to add 10,682 to both sides, and we get 7,630. And that's our answer for part A. Now we're going to sum forces on the person. We'll say the normal force minus the weight of the person, 90 kilograms, times 9.8 equals 90 kilograms, times negative 2.8 meters per second squared. And so then we're going to find 90 times 9.8, 882. And I went ahead and added that to the other side. Minus 90 times negative 2.8, 252. So 882 minus 252 gives 630. Okay, and that's actually the answer for both B and C, because those two forces that you're asked to find in B and C are a third law pair. Okay, and so solution complete. Yes, we answered part D on the first page, on the first part of the video. Signs are all positive, correct units. We didn't talk too much about the units, but it was kilograms times meter per second squared, which is a newton, and then newtons plus or minus newtons, and reasonable magnitudes. Yeah, if we compare these answers to the weights, we see that they're different than the weights, and that's to be expected because the elevator is accelerating. If the elevator had been going at a constant velocity, then we would expect that the values would match those of the weights.